Welcome back, and in this video we're going to be looking at calculating Kc using something called the ICE method. ICE stands for initial, change and at equilibrium. So this is the ICE method. So the first thing we're going to do is write out a balanced equation, and we're going to use that to construct a Kc expression. Remember, the Kc expression will change based on the equation, so it's important that we write that balanced equation first. We're going to construct an ICE table and insert the initial number of moles. We're going to calculate the change in moles and hence the number of moles at equilibrium. And we're going to practice that on page 16 of your notes. We then need to divide by the volume in decimeters cubed to find the concentration. Because remember, Kc is defined in terms of concentration. Now that step is not strictly necessary if the Kc expression has no units, because if the Kc expression has no units, the volumes will cancel. The last step, we're going to substitute our values into our Kc expression and solve it. Remember units. You will always get a separate mark for working out the units. So we're just going to practice on page 16 working out the change and the equilibrium number of moles. So here I've got 1 mole of nitrogen, 1 mole of hydrogen and no moles of ammonia. General rule of thumb, unless you're told otherwise, you can always assume at the start of the reaction initially you have 0 products. We know once equilibrium has been reached we have 0.4 of a mole of ammonia. So the change between the initial and equilibrium is plus 0.4. Well, if this has gained by 0.4 of a mole, the nitrogen must have gone down by 0.2 because the molar ratio is 2 to 1. So if I've gained 0.4 on this side, I must have lost 0.2 on this side. The ammonia to the hydrogen is a 2 to 3 ratio. So again, if this has gone up by 0.4, this must have gone down by 0.6. One side of my equation is always going to go up, and the other side is always going to go down from the initial moles. So let's have a look at another example. I'm starting with 1 mole of nitrogen, this time 2 moles of hydrogen, and no moles of ammonia. Again, because it's a product, I can assume 0. I've gone down by minus 0.9 here. So the nitrogen will have gone down minus by a third of that, 0.3. And the ammonia will have gone up by 0.6. So at equilibrium, I've got 0.7 moles of nitrogen, 1.1 mole of hydrogen, and I've got 0.6 moles of ammonia. One more example. So here again I have my initial number of moles, I have no moles of hydrogen iodide, and I've been told that at equilibrium I have 0.6 of a mole of hydrogen. In other words, it's changed by minus 1.4. This is also changed by the same amount because it's a 1 to 1 ratio, and the hydrogen iodide must have gone up by double that amount, 2.8. So I have 0.6 and I have 2.8. So those are my number of moles at equilibrium. So just working down that page, just calculating the change and the number of moles at equilibrium given our values. And that's an important skill. And this is why we always construct an ICE table, ICE, to help us work out the number of moles at equilibrium. So we're going to have a look at a couple of examples of this. So the first example, I've got a mole of PCl5 decomposing or dissociating into chlorine and PCl3. So the first thing I'm going to do is write out my balanced equation. So I've got PCl5 and it's decomposing to form PCl3 and chlorine gas. And I'm going to just check that's all nicely balanced. I can use that to write my Kc expression, and that is going to be the concentration of my PCl3 times the concentration of my chlorine divided by the concentration of my PCl5. I'm going to construct a little ice table, I, C, and E. So initially, I have 1 mole of PCl5. Because they're products, initially at least, I can assume I've got no PCl3 and no chlorine, because none of this has dissociated. I'm told that after equilibrium had been reached, 32% of the PCl5 had dissociated. So 32% of 1, that gives me minus 0.32. Now, because it's a 1:1:1 ratio, that will give me plus 0.32 here and plus 0.32 here. So I can work out my moles at equilibrium, and that is 0.68, 0.32, and 0.32 there. I need to work out my concentration. So to do that, I'm just going to divide through by the volume in decimeters cubed, and that is 200. Again, it's given to me in the question. I do need to use it in this case because these units don't cancel. If you work out the units, they work out as moles dm to the minus 3. So because I have units, I need to do the concentration. I need to divide through by the volume. So I get 0.68 divided by 200, 0.32 divided by 200, and 0.32 divided by 200. I would usually then go on and work that out just as a separate step. Now I've got my concentrations, I can sub them into my Kc expression. So subbing those numbers in, I get here my value. Again, I've quoted it to 3 sig figs, and I've given my units. That's my final answer. So let's look at the second example. And in this example, I've got SO3 decomposing. So again, I'm going to write out my equation. I've got SO3 reacting to form SO2 and oxygen. So I don't have halves, which is quite difficult to use in my equation. I'm just going to times everything up by 2. Again, I can write out my Kc expression. So Kc is the concentration of SO2 squared times the concentration of oxygen divided by the concentration of SO3 again squared. I can construct my ice table, I, C, and E. Initially, I have 0.02 of a mole of SO3. Initially, because they are products, I can assume I have no oxygen and no sulfur dioxide. I am told that 29% of the SO3 had decomposed. So 29% of 0.02 gives me minus 0.0058. On this side, that will give me plus 0.0058, and because the oxygen is half of that value, it will be plus 0.0029. So at equilibrium, I've got 0.0142, and then I've got the 0.058, 0.0029. Again, because my units don't cancel, I do have to work out concentration, so I'm going to divide all these numbers by 1.5. And again, I'm going to sub those into my Kc expression. So I put them into my Kc expression, remembering to square the SO3 concentration term and the SO2 concentration term, because they're squared in my expression. And again, I've calculated it and I've remembered to use units. The last examples are in your notes and we're on page 18. And these are the most complicated type that you're going to get because they involve a small amount of algebra. So this is my reaction, carbon monoxide reacting with water, or steam in this case, to form carbon dioxide and hydrogen. Again, I have no moles of carbon dioxide and hydrogen initially because they are products. And initially, I have from my equation 3 moles of carbon monoxide and 3 moles of steam. Now in this case I'm not told what my change is or my moles at equilibrium, so I can let X stand for the change. So this side is going to go down and this side is going to go up. So at equilibrium I have 3 minus X, 3 minus X, and I have X and I have X. I can again write my expression for Kc, and that's going to be the concentration of CO2 times the concentration of hydrogen divided by the concentration of CO times the concentration of steam. Now because the units cancel in this case, I don't need to divide through by the volumes, so I can sub in simply the equilibrium number of moles. So I know that my Kc value at this temperature has a value of 4, and I can put these values in. So I have X times X over 3 minus X times 3 minus X. Well, that you can kind of simplify it to X squared divided by 3 minus X squared. If I take the square roots of both sides, square root of 4 will then equal X divided by 3 minus X. Just basically doing a little bit of rearrangement, I get X equals 2. Similar process for the second example. In this case, I have got initially 2 moles of hydrogen and 2 moles of iodine. I can assume, again, no moles of hydrogen iodide. Again, if this side is going down by X, this side must be going up by 2X, because it's a 1 to 2 molar ratio. So I get 2 minus X, 2 minus X here. So I have, in terms of my Kc expression, my hydrogen iodide squared divided by concentration of the hydrogen times the concentration of the iodine. Again, the units cancel, so the volumes will cancel, so I can use equilibrium number of moles in place of concentration. I know that my Kc value is equal to 49, so I have 2X all squared divided by 2 minus X times 2 minus X, which is the same as saying I've got 2X squared over 2 minus X squared. Again, take the square root of everything and I get 2X divided by 2 minus X on the bottom. Again, all I'm going to do is rearrange and solve for X. So I get X is equal to 14 divided by 9. Just as a quick aside, I'll just show you how I rearrange this to make X the subject and work out what it is. So the square root of 49 is 7. I'm going to bring this value up to the top, because if it's divide on this side, it's going to be multiply on this side. In other words, I'm going to multiply through by 2 minus X, and I get 7 times 2 minus X is equal to 2X. So that, timesing everything inside the brackets, is 14 minus 7X is equal to 2X. So again, I'm going to rearrange this and get all my X's on one side and all my numbers on the other side. So I've got 14 equals 9X, because I'm going to bring this minus 7X over this side to become plus 7X, and therefore X is equal to 14 divided by 9. And that equals 1.55 reoccurring. So at equilibrium, I have 2, my starting amount, minus my change, my X, and this will give me my number of moles, or my moles per decimeter cubed for each of those. Notice I can't leave it as a fraction. We never leave our answers as fractions in chemistry. We will always give our answers to a specific number of decimal places. The last bit of the notes were on page 23, and it's just a little extra activity looking at the difference between heterogeneous and homogeneous equilibria. Heterogeneous basically means that my equilibrium mixture is in more than one phase. Now, quite often phase is used interchangeably with state, but they are actually quite different, and we need to understand the difference between the two. So the best way of thinking about this is to be thinking about two containers all containing liquids. So in container 1, I have two liquids. I have oil and water. And in the second container, I have water and alcohol. Now, because the oil and the water don't mix, they're in two separate phases. They are both liquids, so they both have the state of matter of a liquid, but they are in different phases. And that's because if I took a sample from this part of the container, it would have different physical properties than if I took a sample from that part of the beaker. So the different phases are going to have different physical properties. You can usually tell the phases by looking for what we call a phase boundary. So that's a clear separation between the two phases. You can see here we've actually got two phase boundaries, one between the oil and the water and one between the liquid and the air. In the water and alcohol, however, it doesn't matter where I take my sample from, it's going to have the same physical properties. There's only one phase boundary, and that is between the solution and the air. So the easiest way to tell if you've got different phases is to look for the boundary. If you can see a boundary between the two compounds, they're generally in different phases. So a heterogeneous is where more than one phase is present. A homogeneous is where only one phase is present. And in the last part of this, just a little reminder about writing Kc expressions. Do you remember we don't include solids and we don't include solvents. Solids because they don't change concentration, their concentration remains constant throughout the experiment, and solvents for the same reason. The concentration of the solvent will remain unchanged. So in this first example, it's this carbon you need to be aware of. In the second example, it is both the calcium carbonate and the water because the compounds are aqueous. So neither of those and that will not appear in my Kc expression. So this Kc expression here does include the water because the water is not a solvent. Everything is in the gas phase, but we've missed it out here because although it's liquid, it is found in these aqueous solutions. So that's the Kc expression for that equation. So that finishes this section on calculating Kc. And that finishes, in fact, this whole pack, with the exception of the practicals, which we're obviously going to do in class. But you should have all the information you need now to start answering the questions at the back of the pack. So until later, take care, stay safe. Bye-bye.